We are told that surviving the world's most hostile terrain requires massive steel axles, locking differentials, and heavy combustion engines. But while Western automakers spend billions refining 100-year-old analog hardware, a Chinese military manufacturer just proved that the ultimate off-road vehicle does not use physical axles at all. For decades, the global expedition market has been defined by a very specific, brutal compromise. If you wanted to carry the heavy living quarters of a motorhome into the deep wilderness, you had to accept that your vehicle would eventually get stuck. Traditional four-wheel drive systems, whether built by Ford, Land Rover, or Mercedes, rely on a central spinning drive shaft that mechanically forces power to the front and rear wheels. When a multi-ton camper hits deep mud or snow, this analog system inevitably wastes its energy by spinning the tire with the least traction, burying the heavy chassis deep in the dirt. To survive the backcountry, overlanders were forced to pack heavy recovery gear, steel winch cables, and hope they never encountered a river deep enough to flood their combustion engine. But deep inside the testing grounds of Dongfeng, a major Chinese defense contractor, engineers completely discarded the concept of the mechanical truck. They took their classified Mengshi platform, a heavy, armor-plated tactical vehicle designed to survive extreme combat environments, and adapted it directly for the civilian expedition market. Instead of bolting a larger diesel engine onto thicker steel axles to fight the terrain, they stripped the mechanical drivetrain away entirely. They replaced the legacy hardware with a quad-motor digital architecture, giving every individual wheel its own dedicated electric brain. The result is a massive motorhome that can instantly calculate its own traction, execute a flawless 360-degree tank turn on a narrow mountain trail, and if it plunges into a deep river, completely seal its hull to physically float across the water. This is the shift that is currently terrifying legacy automakers. By treating a multi-ton motorhome exactly like a highly advanced digital drone, this technology completely eliminates the physical limits of extreme overlanding. Think about the fundamental lie of the modern recreational vehicle industry. When a consumer purchases a premium off-road camper, they are sold the illusion of absolute geographic freedom. The marketing brochures promise the ability to escape crowded electrical grids and park comfortably on the edge of untouched mountain cliffs. Yet, the reality of overlanding is often a grueling exercise in logistical anxiety. Driving a heavy, top-heavy vehicle far beyond the reach of cell phone towers or emergency tow trucks introduces a massive element of physical risk. If a single steel differential snaps on jagged rocks, or if a sudden flash flood raises a river crossing above the vehicle's mechanical weighting depth, a luxury vacation instantly becomes a dangerous survival situation. When a vehicle relies on a standard combustion engine, it fundamentally requires air to function. If water enters the air intake, the engine suffers hydro-lock, a catastrophic failure where the internal metal pistons violently shatter against incompressible water, instantly destroying the motor. Because of this inherent physical weakness, traditional overlanders must obsessively map their routes to avoid deep water and deep mud, restricting their geographic independence to well-worn dirt roads. If you are into stories about technology changing the world in ways nobody expected, hit that like button and subscribe. Now, picture an industrial system where the fear of mechanical failure is entirely removed from the equation. When a manufacturer eliminates the central engine and the connecting drive shafts, they erase the primary points of failure that strand traditional vehicles in the wilderness. An overlander operating a digitally driven quad-motor chassis no longer needs to calculate the precise depth of a river crossing or worry about snapping an axle under the heavy weight of the living cabin. The vehicle operates with the relentless redundancy of an aerospace vehicle. If one motor loses traction on a slippery boulder, the central computer instantly redirects power to the other three tires, seamlessly pulling the massive structure forward without any driver hesitation. In real terms, this completely transforms the psychology of off-grid exploration. The heavy expedition vehicle stops being a fragile mechanical liability that you have to carefully nurse through the wilderness. Instead, it becomes a heavily armored, hyper-capable survival pod. For the global automotive industry, the implications of this shift are fatal to the old guard. The brands that have spent a century mastering the art of bending steel and tuning diesel engines are suddenly competing against a defense contractor writing flawless traction algorithms. The race to dominate the extreme expedition market is no longer about building a stronger truck. It is a quiet struggle to digitize the dirt itself. To understand why the expedition vehicle had to be digitized, we have to look at the historical failure of the mechanical drivetrain. For over a century, the global off-road industry treated the automobile as an analog machine bound by the physical limits of steel and combustion. The standard playbook for surviving extreme terrain was simply brute force. If a 4x4 truck got stuck in the mud, legacy Western engineers would add a heavier diesel engine, bolt on thicker steel axles, and increase the size of the tires. But as humanity tried to push heavy living quarters deeper into untouched wilderness, that traditional mechanical method hit a literal wall. The physics of raw terrain defended itself through three distinct layers of mechanical failure. The first layer is the biological weakness of combustion. A traditional diesel engine is essentially a mechanical lung. It requires a constant, uninterrupted flow of oxygen to generate power. When an overlander attempts to cross a deep river, the heavy water inevitably surges over the hood. If even a small amount of that liquid breaches the air intake, the engine undergoes catastrophic hydro lock, shattering the internal metal pistons and instantly killing the vehicle. Furthermore, as these heavy rigs climb into high-altitude mountain ranges, the thinning atmosphere starves the engine of oxygen, severely reducing the horsepower exactly when the driver needs it most to pull the heavy living cabin up a steep incline. The second layer is the physical limitation of the solid axle. When you load thousands of pounds of reinforced camper shells, water tanks, and solar batteries onto a standard truck chassis, you place an immense gravitational burden on the drivetrain. As the vehicle crawls over jagged boulders, that massive weight is repeatedly slammed down onto the physical steel axles connecting the wheels. Eventually, under the extreme torsion of rock crawling, even the most hardened steel warps, fractures, and snaps. When a mechanical axle breaks miles away from civilization, the vehicle is permanently immobilized, turning a minor structural failure into a life-threatening crisis. The third and most fatal layer is the mathematical failure of the mechanical differential. In a traditional four-wheel drive system, the engine sends power down a central spinning drive shaft, which then uses mechanical gears to split that power between the tires. When one side of a heavy motorhome sinks into deep mud while the other remains on solid rock, the analog gears cannot adapt. The mechanical differential blindly sends the engine's power along the path of least resistance. It rapidly spins the tire trapped in the mud, digging the multi-ton vehicle deeper into the earth, while the tire on the solid rock remains completely motionless. Mechanical overlanding was a physical dead end. The entire expedition industry was stuck. The breakthrough did not come from traditional automotive design studios in Detroit or Germany. It came from a highly technical engineering insight at Dongfeng, China's premier military contractor. These defense engineers were not looking at off-road traversal as an automotive problem. They were looking at it as a digital logistics failure. They realized that the only fundamental difference between a stranded truck and a highly maneuverable aerial drone was the reliance on a centralized engine. A quadcopter drone does not use a central motor to spin its rotors through complex gears. It uses 4 independent motors, controlled instantly by a central computer. Instead of trying to forge a stronger steel axle, these military engineers decided to digitize the drivetrain entirely. They developed the Mengshi off-road architecture, stripping away the vulnerable drive shafts and heavy differentials and bolting a high-output electric motor directly to each individual wheel. The solution to the heavy expedition crisis was not building a tougher analog truck. It was eliminating the mechanical axle entirely. To bypass the structural failures of traditional off-roading, Chinese military engineers abandoned the single centralized engine. Instead, the vehicle utilizes a distributed powertrain consisting of 4 completely independent electric motors mounted directly to each wheel hub. This quad-motor system produces a combined output of 1,088 horsepower. In a traditional internal combustion vehicle, Generating that level of horsepower requires a massive, heavy multi-cylinder engine block that occupies half the chassis and demands a complex network of cooling lines. Here, the power is delivered by compact, high-density, permanent magnet synchronous motors. These units are encased in high-strength aluminum housings that resist both extreme physical impacts and thermal stress. Because there is no physical driveshaft or central differential connecting the front and rear of the vehicle, the heavy steel linkages that typically break under load are completely absent. Power travels from the main structural battery pack to the wheels entirely through thick, heavily insulated, high-voltage electrical cables. In real terms, this architecture grants a heavy, fully loaded motorhome the acceleration profile and raw physical power of a modern hypercar. A vehicle weighing several tons can effortlessly ascend 60-degree dirt inclines without any of the engine straining or transmission overheating that plagues conventional overland rigs. The engineering tolerances of these hub-adjacent motors require a completely unique thermal management strategy. When 4 separate motors are generating immense horsepower under low-speed, high-load conditions, such as crawling through thick mud, they generate massive amounts of localized heat. Dongfeng engineers resolved this by integrating an active liquid cooling loop directly into the motor housings. A specialized multi-channel cooling jacket surrounds each motor stator, constantly circulating a water glycol mixture to draw heat away from the copper windings. This fluid is pumped through reinforced flexible hoses back to a central, heavy-duty radiator array mounted at the front of the vehicle. The entire system is hermetically sealed to prevent any mud, grit, or dust from penetrating the cooling channels. This ensures that even when the vehicle is working at its absolute thermal limit in 40-degree desert environments, the motors remain within their optimal operating window. In plain English, this cooling system works exactly like a high-end gaming desktop computer that uses liquid-filled tubes to constantly pull heat away from a stressed graphics card during heavy processing. The vehicle can maintain its full torque output indefinitely without entering a protective limp mode. Eliminating the physical axle meant that traction could no longer be managed by mechanical gears. Instead, the vehicle utilizes a central electronic control unit that executes advanced digital torque vectoring. This system calculates the exact grip, slip angle, and rotation speed of each individual tire hundreds of times per second. When a traditional expedition rig encounters uneven terrain, the driver must manually engage mechanical differential locks, which rigidly bind the left and right wheels together. If the vehicle turns sharply while these locks are engaged, the tires chirp and binding forces place immense stress on the axles. The digital system entirely replaces these mechanical locks with lines of code. If the onboard sensors detect that the rear left wheel has lost traction on wet clay, the computer instantly cuts power to that single motor in a millisecond. It simultaneously redirects that extra electrical energy to the other 3 wheels that still possess physical grip. In real terms, the vehicle essentially thinks its way out of the mud faster than a human driver could even react to a slide. The twisting force is applied with absolute mathematical precision, ensuring no energy is wasted spinning tires fruitlessly. The raw force behind this digital management is a staggering 16,000 Newton meters of total wheel torque. In standard mechanical vehicles, torque must travel through a transmission, a transfer case, a drive shaft, and a differential gear set, losing efficiency at every single step due to physical friction. Because the quad motors are mounted directly at the wheels, this massive twisting force is delivered with 0 mechanical delay. The central computer can modulate this torque from 0 to 100% on any single wheel instantly. To withstand this immense rotational strain without shearing the wheel hubs off the vehicle, the suspension arms and steering knuckles are forged from military-grade, high-strength structural steel. The internal bearings are oversized and treated with a specialized low-friction coating to handle continuous, high-torque loads. In plain English, the digital torque output of this single vehicle possesses enough raw twisting force to snap a traditional commercial truck's steel drive shaft completely in half. Yet, because it is managed entirely by software algorithms, it can gently nudge a multi-ton camper over a fragile sheet of ice without breaking it. The independence of the 4-hub motors allows for steering and movement profiles that are physically impossible for traditional mechanical vehicles. By utilizing an advanced 4-wheel independent steering system, the vehicle can execute what engineers call a crab walk. In a standard off-road vehicle, the front wheels turn while the rear wheels remain rigidly parallel to the chassis. This means that to move sideways or navigate around an obstacle, the truck must move forward or backward in a curved arc. The quad motor platform allows the rear steering actuators to turn the back wheels to the exact same angle as the front wheels. When the driver applies throttle, all 4 wheels rotate in the same direction, allowing the massive expedition rig to slide diagonally across the terrain without changing the orientation of the main chassis. In real terms, this allows a wide, heavy motorhome to effortlessly maneuver through tight, dense forests or narrow, rocky canyons. The driver can simply slide the vehicle sideways around a jagged boulder, eliminating the need to back up or risk scraping the expensive living quarters against the scenery. The ultimate expression of this digital drivetrain is the zero-radius tank turn. To execute this maneuver on traditional tracks, a bulldozer locks one side while driving the other forward. In this wheeled vehicle, the process is handled entirely through independent motor rotation. When the driver activates the tank turn feature on a narrow mountain pass, the central computer commands the 2 left motors to spin backward, while simultaneously forcing the 2 right motors to spin forward. The specialized high-traction tires slide against the ground, rotating the multi-ton vehicle around its own central vertical axis. To prevent the tires from violently tearing themselves apart or damaging the electric motors during this high-friction turn, the computer continuously monitors the surface resistance, pulsing the torque to allow just enough slip to let the chassis rotate smoothly. If a human engineer sat down and attempted to manually coordinate the 4 separate throttles, brake pressures, and steering angles required to rotate a multi-ton truck in place, it would take them lifetimes of constant adjustment to prevent the vehicle from rolling over. Here, a single microchip handles the entire calculation in the background, spinning a massive mobile home around like a toy. As extraordinary as this distributed quad-motor architecture and digital torque management system is, it is still just a collection of smart motors bolted to a heavy chassis. When you look at the entire vehicle, the massive high-output magnet synchronous motors, the complex active liquid cooling loops, the 16,000 Newton-meters of raw twisting force, they look like separate, impressive off-road capabilities. But there is a hidden, structural masterstroke that connects all of them. The true breakthrough of this amphibious expedition platform is not its ability to claw through deep mud or climb extreme rocky mountain passes. It is how these military engineers managed to solve the most fatal problem in the history of heavy overland exploration: the sudden transition into unwadable deep water. Remember that a traditional heavy motorhome is fundamentally a sinking liability when it encounters a deep, flooded river crossing. If the water level rises past the bumper, the vehicle loses traction as the tires float off the riverbed, the heavy current sweeps the multi-ton cabin downstream, and water floods the mechanical components. Traditional off-roaders fight this by adding raised snorkels or increasing ride height, but they are always limited by gravity and the physical depth of the water. The Amphibious system completely bypasses this limitation. When the vehicle enters a river that exceeds its standard 1.2-meter wading depth, the central computer does not panic or shut down. Instead, the vehicle's onboard sensors instantly detect the loss of ground resistance and the sudden displacement of weight, triggering an emergency hermetic seal across the entire lower hull. The chassis functions exactly like a welded steel boat hull, trapping air inside to achieve immediate positive buoyancy. The tires leave the ground. The hull floats perfectly. The motors switch functions. This is the exact puzzle piece the legacy automotive sector missed entirely. The absence of a physical mechanical axle does not just eliminate moving parts that can break under load. It creates a completely open, unobstructed undercarriage that allows the spinning, deeply treaded tires to act as dual-sided high-speed paddle wheel propellers. The vehicle does not fight the water by trying to stay heavy. It conquers the river by transforming into a motorized vessel, fundamentally altering the survival limits of global overlanding forever. If this military-grade quad motor and buoyant hull technology successfully scales across the global civilian recreation and utility markets, the traditional dominance of Western off-road engineering will be permanently broken. To understand the immense scale of this paradigm shift, look at history. When the United States mass-produced the Willys Jeep during World War II, it did not just build a new vehicle, it established a universal, rugged mechanical standard that allowed Allied forces to move across any broken terrain, eventually spawning the entire modern global 4x4 automotive industry. The quad-motor Amphibious platform executes the exact same maneuver, but for the digital era. By allowing a heavy multi-ton vehicle to navigate extreme terrain without a single physical axle, old mechanical constraints stop being an operational barrier. Western automakers that currently hold strict monopolies over legacy luxury overlanding networks rely on their decades of experience tuning analog gearboxes and strengthening steel differentials. If a consumer or a military logistics team can simply purchase a digitally managed, self-sealing chassis that floats across rivers and executes tank turns on narrow cliffs, the traditional engineering advantage of legacy automotive empires becomes completely obsolete overnight. Now, here is the honest concession. Today, this highly advanced quad-motor architecture introduces a real significant systemic vulnerability. While the elimination of physical driveshafts removes mechanical points of failure, the entire platform is completely dependent on a massive, highly complex electrical grid of high-voltage wiring, automated sensors, and real-time computation. If an overlander suffers a severe electrical short circuit deep inside a remote jungle, or if a jagged rock manages to slice through the heavily insulated high-voltage cables powering a wheel hub, the vehicle cannot be repaired with standard hand tools or basic mechanical knowledge. It remains a highly vulnerable, specialized digital system that demands advanced diagnostic software to troubleshoot in the field. But do not mistake early electronic vulnerabilities for a reason to doubt the overarching trajectory. The physical limitations of traditional analog 4x4 systems mean that the mechanical ceiling for combustion-based overlanding has been reached. While conventional automotive brands continue to spend billions of dollars trying to squeeze slight efficiency gains out of traditional steel axles and locking gears, the future of extreme geographic survival is moving directly onto digital platforms. The ultimate transition will not require packing heavy steel recovery winches or fearing deep river crossings. It will simply require driving a digital drone directly through the water. As universally accessible algorithms allow multi-ton mobile homes to float across rivers and rotate in place, which traditional Western automotive giant will collapse first? Drop your answer below.